Welcome to Podcast 5.1, a new chapter, a new podcast, and you will find there is a lot of material in here that we've talked about in the past. I've alluded to in other podcasts, and some of it's going to be familiar, so it's going to be quite easy to grasp this stuff, I think. Well, the first thing I want to look at is this title, Chemical Reactivity, because that's kind of what this chapter is about. And really it stems from the fact that when you have an atom that has lost or gained an electron, it reacts a little different way and is attracted to things of opposite charges. So we want to talk about how this chemical reactivity comes about and what are some things that we know. And since we know electron configuration, hopefully it'll make sense. Well, look at this thing right here. Noble gases are least reactive. All right. Well, I think we've mentioned that. I've told you that's why they're called noble and all that stuff. But why is that? Well, it turns out that noble gases have 8 valence electrons. Or another way to think about it is they have full s and p orbitals. And just as a kind of a quick review, if I were to look at the periodic table, right, and I were to count all the way over here to the noble gases, I would just go 1, 2, 3, 4, 5, 6, 7, 8. They all have 8 valence electrons, which leads me to the next thing, this word right here, octet rule. Okay, octet rule. And the octet rule is simply this. Atoms tend to gain or lose electrons until they have a full s and p orbitals. Now, if you think about that, you know you could put 2 electrons in the s orbital. So we could put 2 electrons there, and we could put 6 electrons in the p orbitals, and that gives us 8 electrons, right? So the octet rule is kind of the driving force on why a lot of this chemical reactivity takes place. So look at this next statement I have right here. Halogens and alkali metals are the most reactive. Do you know why? I think we might have talked about it before, but if you don't know why, take a minute, look at the periodic table, and think about it. Well, what do I know about all of these elements right here in the alkali metal group? What do we know about all those? We know they all end in S1. They have 1 valence electron. What do I know about all these halogens right here? We all know that they end in P5. All right? Well, if these halogens gain 1 electron, and fluorine, for example, has 9 electrons. If it gains 1 electron, it has 10 electrons, and that gives it an electron configuration of P6. And what do we know about electron configuration of P6? Well, it's very stable. It's a noble gas. What about something like potassium with this S1 electron? It's 4s1, right? Well, if it lost this S1 electron, it would only have 18 electrons, right? Who has 18 electrons? Argon has 18 electrons. So if the potassium atom loses an electron, it has a noble gas electron configuration. And we know from the past that that's a very stable situation. So that makes these guys the most, that makes these 2 columns the most reactive. So the halogens gain, so the halogens gain an electron, and the alkali metals lose an electron, and that allows them to have an octet. And when you have an octet, you are a more stable, you're more stable energetically. All right. Okay, on to our next little slide here. Let's talk about valence electrons. Oh, wait, we already know about valence electrons. We sure do. So this is just a quick review. If you want to write it down, fine. If not, that's okay. As you recall, we just count the elements in the S and P block along the period. And I've already done it once this podcast. I'll do it again in this podcast. So if I was going to find the number of valence electrons in something like phosphorus, it would be 1, 2, 3, 4, and 5 valence electrons, right? Remember that stuff? Hope you do. Move it on. Okay, now, one of the things I just talked about is that elements will either gain or lose electrons to become an octet. And that is an important thing because what that does is it changes the atom. It's no longer an atom, it's an ion. And the definition for ion is pretty straightforward. It's an atom that has lost or gained an electron. And so my question to you is just a little review. Why is that? Why did it lose or gain an electron? And that was so it could get an octet. Right? So you could probably look at the periodic table and you could look at something like these guys over here, beryllium, magnesium, calcium, and so on. And you can imagine how many electrons they might lose or gain. Well, beryllium can either lose 2 to have, well, that's not a duet, right? Because helium has a duet. Or it could gain 6. Well, what's probably more likely, losing 2 or gaining 6? And the answer is, of course, losing 2. And you could figure out something like this. What about sulfur? All right? What's sulfur going to do? Well, it has a choice. It can either gain 2 electrons to be like argon, or it can lose 6 electrons to be like neon. Energetically, which one's more likely? Gaining 2 electrons. Right? That's kind of an important thing because it leads us to understand how these charges occur the same way with each element. But let's go through a couple more words. We have 2 terms. One when you have gained an electron and one when you have lost an electron. This first one is a cation. I know a lot of people call that cation, but it's an ion with a positive charge. And for an ion to have a positive charge, it has to have lost an electron. Now let me tell you, this messes people up because we don't usually associate the word lost with positive, right? We usually associate loss with negative. But let me give you an example. Let's say I have sodium. All right. Sodium, if we look on the periodic table, we know it has 11 electrons, right? It also has 11 protons. So sodium has 11 protons and 11 electrons, okay? However, what's it going to do? Is it going to lose this S1 electron, or is it going to gain 7 electrons? Well, obviously, it's going to lose that 1 electron. So now, it still has 11 protons, but it has 10 electrons. Okay? Well, if I've got 11 positives and 10 electrons, what do I get? I get plus 1. Wow, see how useful algebra is? 11 plus a negative 10 equals plus 1. So a cation has lost something, but it's gained a charge. All right? And just almost the opposite of that, we have an anion. And it has a negative charge. Okay? Negative charge, but it has gained something. And once again, gaining and negative are counterintuitive. So that does seem to be a problem sometimes. Okay, let's look at chlorine. How many electrons does chlorine have? Well, let's find it over here. It has 17. You can't, let me erase some of this gibberish I have here. Okay, chlorine has 17 electrons, right? Well, if it has 17 electrons, it has 17 protons. Okay, and then if we look at the periodic table, what's the likely scenario? Is it going to gain 1 electron to be like argon, or is it going to lose 7 to be like neon? Well, hope you said that's going to gain an electron. Sure it is. So the number of protons is still the same, right? But the number of electrons is increased by 1. So you do a little 17 plus a negative 18 equals negative 1. Right? Does it make sense? Hopefully it does. Because we're going to see these charges for the certain atoms the same all the time. All right, so that brings us to the idea of the characteristics of ions. Now, if I take an atom, and let's say, since we're talking about chlorine, it gains that 1 electron, it's still a chlorine ion, but chemically it almost acts more like argon. Because again, the chemistry that we deal with is really dependent upon the number of electrons. So when we're talking about ions, okay, they have different properties than the atom all by itself, and it's more like the noble gas than the element. In other words, they're not going to be as reactive. A fluoride ion, okay, that's an F minus. Oops, that's an F minus. A fluoride ion is quite a bit different than just a fluorine atom. Okay? Because a fluorine atom wants to find an electron. It wants to gain an electron. Whereas a fluoride electron has already gained it and it has a full octet. So they're going to react quite differently. All right? And then the next thing that's kind of important is what happens over and over and over. And it turns out that elements in certain groups tend to lose or gain the same amount of electrons over and over and over. So that makes it kind of nice because then we can kind of predict and we can actually memorize their charges without really having to memorize. For example, let's look at a periodic table here. What do we know about all these in this row right here? Okay, they all end in S1, right? And so they're always going to lose that electron. And this is something I want you to do with your periodic table right now. So I want you to write +1 at the top of that column. Oh, that's a horrible +1. I wish that 1A wasn't there. +1. Okay. Those guys always gain a charge. What about these? These all end in S2. Well, they're always going to lose 2 electrons. So whenever those metals become ions, they're going to lose 2. So that gives them a positive 2. Now we're going to skip the transition, and for reasons I'll get to later. But let's go to this group 3A. And by the way, don't let this A and B bother you. The main group used to be the A's, and the transition used to be the B's. And just don't let it bother you too much, because since these days, they just call them groups 1 through 18. But I want you to write right here a +3 charge at the top of aluminum's group. And it really is not for boron. It's mostly for aluminum, gallium, indium. All right? But think about this. Aluminum has 3 valence electrons, right? 1, 2, 3. Is it more energetically favorable to lose 3 or gain 5? And hopefully you're thinking, well, it would be more favorable to lose 3, and so therefore it becomes a positive charge. Right? This row we don't write anything. All right, carbon. These guys tend not to form ions. But then we go to sodium, potassium, and sometimes arsenic. Look at what they're going to do. If they gain 1, 2, 3 electrons, they will have a noble gas configuration. So when they gain electrons, what kind of charge do they get? Negative, you're saying? Absolutely right. -3. What about oxygen? If it gains 1, 2 electrons, it'll become a noble gas, so those always form a -2 charge, and the halogens always form a -1 charge. Hopefully that makes sense. If it doesn't, ask me about it tomorrow. I'll do the best job I can to explain it. Okay? And so I've got a little picture of what tends to happen, and this is it right here, just what we wrote, right? Now, there's a couple things about this I don't like. They did do group 3 +3. That's a transition section, but we'll worry about that later. But now you've got these numbers written at the top of your periodic table, and you're going to be able to use that on tests and everything, so hopefully you'll remember those charges. All right, almost done. Now it gets tricky. I said we're going to talk about the transition section because it's a little different, right? Well, here's the problem with the transition elements. Dun, dun, dun. They form ions without complete octets. So it's not something you can go, oh, well, iron, let's go to that. Let's go to my periodic table. Iron's always going to form a +1, 2, 3, 4, 5 charge. Or it's going to form, let's see, a +4 or +3. There's really no way to do it. Oh, palladium's always going to form a +1. It doesn't work like that. These guys in here are not going to lose 5, 6, 7 electrons or gain 5, 6, 7 electrons to make this work. So it kind of makes it a little tough on us because we kind of have to learn a way to, I don't know, memorize what kind of charges they form and come up with ways to name them, and it's going to get a little messy. But we'll get with it. All right? And then here's the other thing that makes it even more challenging. Many form more than one cation. Okay? And I'll show you a picture that demonstrates this. Look at this thing. Look at all the different ions that some of these transition metals make. Right? Here's titanium. Sometimes it's a +2, sometimes it's a +3. Now, exactly why does this happen? All we can say is that energetically they're going to go to the most stable situation. All right, so they do tend to favor one of these states more than the other. But for right now, you just need to know that they form more than one charge. And you really kind of should memorize them. I'm going to show you a way when we name formulas, how to kind of pick up what their charge is. But it's much easier if you know, for example, that iron's always 2 or 3. Or that chromium's always 2 or 3. Or that copper's always +1 or +2. It makes it a little bit easier. All right, and we'll spend some time with that when we start naming compounds. All right, on to the last little bit today. So as a general rule, for all these elements, and this is something I've kind of already talked about, metals always lose electrons to form cations, and nonmetals always form anions by gaining electrons. So again, if you're not sure where that non-metal-metal line is, it's right here where that stair step is. Okay, all the way down to here. So these are the nonmetals. As you can see, I've got it right there. And the whole rest of the periodic table, 75% of the periodic table, are metals. So all those elements are going to form cations. These nonmetals are going to form anions. All right. So like always, bring your questions to me. Hopefully this stuff is making sense. We'll spend some time in this. Don't panic. And I'll see you next time.